Hello everyone, welcome to this presentation on improving malware detection using adversarial attacks in Android system. This research was a part of our final year project and we would like to discuss more about it. As we know, Android has become the leading operating system in the mobile industry. As a consequence of this, a huge user base for the system has become uh, actually a target for the attackers. In order to gain root privileges, these malwares try to disguise themselves amongst the benign softwares. To do this, attackers use several adversarial machine learning techniques to fool anti-malware systems. We propose a method that generates poison samples from benign permissions and attempts to find weaknesses in the system.
So I'll be talking about motivation. So we see that in present age where anti-malware technologies and machine learning models become obsolete and vulnerable rapidly. So it's very important for us to stay one step ahead of threats like hackers who can use white box attack or a black box attack to generate their own attacks and undermine security and detection of malwares. We see ransomwares are like really trending right now. Talking about the white box attacks are those in which the hackers have the access to the model's parameters, and in black box attacks, they don't have access to the model's parameters. So we see a lot of previously used ML approaches face serious security issues and vulnerabilities that the hackers make use of. It is very important for us to come up with a unique and previously unused approach that can help in improving the classifier accuracy. Also, we see newer attack strategies being used increasingly, which the present classifiers are not equipped to handle. Our system is proposed because we make use of such a new approach or paradigm using evaluation of models based on deep neural networks as well as 1D CNN networks. Further, we can also use two different attack algorithms, the reinforcement learning based approach and the deep learning based GAN or GAN approach. These models will be compared with three data sets, and the attack and the defense method will be validated and tested. The models will be tested before and after the adversarial attacks on different classification models. Talking about the previous methods, so we see GAN or GANs or generative adversarial nets. So they are based on zero sum non-cooperative game, which follows the minimax algorithm. The objective is basically to maximize the loss function of the discriminator or the classifier model and minimize the loss on the generator, which will generate the adversarial samples. There was a paper on detection of adversarial samples, which gave a new hypothesis basically to identify adversarial inputs based on the classifier output, which was then validated by using statistical tests such as fast gradient science and saliency map algorithms before they are fed to the ML model as inputs. The approach was exciting, but then they didn't exactly present a countermeasure to combat such adversarial attack. Talking about Q-learning. So Q-learning is in reinforcement learning. It's a value-based reinforcement learning algorithm which is used to find the most optimal action selection policies. The goal of the Q-learning is to maximize the value function. The Q table helps to find the best action for each state. So basically, in the given diagram, so if you are on a particular node, so it'll select the optimal path for reaching a destination node. Talking about 1D CNNs, so they have a lot of advantages. They can work real time. They have a low cost hardware implementation which can improve its feasibility. When it comes to poisoning attacks against SVMs, so SVMs we know are basically used for classifying. So if we can tamper with the data that we feed as input data set, so that can really hamper with the results. Evading anti-malware engines with deep reinforcement learning. So there's work going on the proposed DQEAF, which will be evaluated by other families of malicious software, which can show code robustness.
Here are some details on the methods. We propose two methods that will help generate adversarial attacks. The first is a reinforcement learning based method where we use Q-learning as our base. The second one is a GAN based attack that we change for this format. Uh, we also propose to retrain the model with the poison data and see what improvements we gain on the data sets after retraining it on the poison data. So we'll go on to our Q-learning method. In our Q-learning method, we define a state, reward, and action. The Q-learning objective is just as we've seen in textbooks. In the state definitions, we have S is equal to F0, F1, all the way till Fn, where each or Fi can be either 0 or 1. So F represents the malware's permission. Malware can, the permission can either be off or it can be on. And now we go on, move on to the reward function, which is alpha times the classifier's result minus beta times the summation of how many states were changed. So if the classifier's result is, for example, benign, we give the classifier out value of one. If the classifier was still malware, we give the classifier's output as minus one. So what we're trying to do here is give a positive reward if the uh, if our agent is able to fool the classifier. That's when we give it one, and if it's not able to fool the classifier, we give it a value of minus one. So of course, the higher the reward, the more it'll try to align itself to that type of goal. So alpha and beta, by the way, are tunable parameters. They range between 0 and 1. So that will define how important we want it to be. The summation of the permissions changed. So the number of permissions changed should be very less in the beta part. So that's why we subtracted with this classifier. So in action space, the agent has a choice to choose 0 or 1 if the bit is not already set to 1. If the bit is already set to 1, the malware might actually need that permission in order to get access of the root privileges. That is why if fi is equal to 1, we set it as 0, as in we will not be, the agent will not flip the bit. Otherwise, it has the choice to flip the bit, which is 0, or not flip the bit, which is 1. And of course, the Q-learning objective is, as we see in standard textbooks, used for optimization of the agent. So before we start, I would like to talk about how normal GANs work for the GAN approach. In a normal GAN, we have random noise that's passed through a generator, and it generates, in this example, it's generating some faces. It's comparing, the discriminator will compare the real faces to the generated faces and choose which one is real. Of course, at the starting, the real faces will be an easy task. It'll be an easy task to distinguish the real faces from the generated faces. But as the model gets more optimized and back propagation happens multiple times with various examples, it will become harder and harder to distinguish between the real and the generated face, up to a point where the discriminator will be basically guessing 50-50 which one is the real and generated face. This was a motivation to for our model, our GAN model. So in our GAN model, we have a benign vector, and our malware vector goes through the generator. The generator perturbs it such that it looks as much as it can like a benign sample, and the discriminator compares the benign sample and the malware sample, which has been perturbed. So at the starting, it's easy for the discriminator to choose the benign model, but as epochs progress, we are able to see that it starts choosing the GAN model just as likely as the benign model, the benign vectors. Our input feature vector is the malware model that we're trying to perturb to make it look like it's benign. We pass it through a deep neural network, we pass it through one DCNN, and we basically concatenate the vectors. We pass it through a softmax function, and a new feature vector is generated. So according to the outputs of the discriminator, these models will change. These models will change their weights, and hopefully it'll produce good results, which it does, as you'll see later on. And we use a simple GAN loss function, as you can see here, and our algorithm is listed as below.
The scope of our project follows the ideology that generating better adversarial attacks will ensure that we will successfully breach the malware classifiers, which in turn mean we will be able to train the newer models to better safeguard against variety of attacks. We will demonstrate the attacks over two virtualized nodes, an untrained default node and a retrained model. This is done using React web-based application spanning over multiple pages. We use vector diagrams to portray the attacks, which can then be used in statistical analysis of the outputs of both models. Our web app will have a custom generation module which will enable the users to create their own manual patterns and input to both the models. The inputs would then be stored along with the dataset which resides in the SQL database connected to the Node.js backend. So let's come to our results. We tested adversarial attack strategies on four most widely used malware detection models, namely logistic regression, support vector machines, random forest classifiers, and deep neural network classifiers. With our attack based on reinforcement learning, we see the model accuracy drop by 6 to 7% in logistic regression and support vector machines, and a huge drop of around 35% in random forest classifiers, meaning that random forest classifiers are more susceptible to adversarial attack samples. We see slightly better performance with our attack based on GANs. On retraining with our perturbations, we see a significant increase in detection accuracy for adversarial attack samples as shown in the graph. Now let's discuss about the applications of our project. Successfully breaching the malware classifiers give up adversarial perturbations that can be reused to train existing models. The model can be used by students, developers, algorithm testers to learn how ML algorithms may be used for or against malware detection systems. The developers in charge of the security at Android can use this system to reinforce against such attacks. Domain experts may use these results to develop more innovative models based on this model. Let's now talk about the limitations of our project. As the number of permissions for an Android app range in about 200 permissions, thus contributing to more parameters, which in turn leads to more time and resources required for training and evaluation of the model. Another limitation that we faced are some approaches used in our model are fairly recent and thus are being still explored. In conclusion, our system presents two novel methods of generating adversarial samples that breach in widely used malware detection algorithms, which in turn helps us create a model robust against such attacks. Here are some of the references that we used. Thank you.